Okay, this is part 4 of our videos. So just back to this table where I'm collecting the analogous parameters from angular motion to in translational motion. So we've added, we've got rotational kinetic energy, we've got torque, net torque, which functions as the thing that produces our acceleration, just like net force produced translational acceleration. Net torque produces angular acceleration. Work done by a force or a torque. Work done by a force is just, if you have a constant force, it's going to be the force dotted with the displacement. And here we have a torque dotted with the angular displacement. Again, the analogous component to force, which is torque, and the analogous component to displacement, which is delta theta. And then the work kinetic energy theorem is still the same. So however much kinetic energy you have initially minus finally, or finally minus initially, that's your net work, where the net work could be the work done by torques, not just the work done by a force. And the book has got, a version of that over here. Again, sort of, what are we talking about? How are they compared to each other? All right, so there's one last translational parameter that we just did back in chapter 9, which is linear momentum. So linear momentum was little p, and it's a vector, and it was the mass times the velocity. There's sort of two different situations here with angular momentum, and your book writes one, they're both L, but one is a little letter L and one is a capital L. And this is actually in chapter 11. Let's see if I can go find our discussion for angular momentum. So, goodness. Yeah. Maybe I can't find it. Torque, you know what, we're just going to make that small and we'll make this bigger right now. So angular momentum it's the correspondent to this. So you can have angular momentum for sort of a small particle, an object that's moving around something else, right? So we could have, as we've done before, if we have, some object that's moving on some circular path around some central location here, so it's moving like this along that object can have angular momentum because of that. But you could also have angular momentum for a system or a large object, and that's usually written as capital L. And just as when we did, we talked about Newton's second law in terms of momentum, that's what this is. So this is Newton's second law in terms of momentum instead of mass and acceleration. We can also say that, so the second law says that it's the derivative, the time derivative of momentum. With here, the net torque, because that's what stands in for net force, is the time derivative of angular momentum, whether it's little l or capital L, depending upon whether you have what situation you've got. And just as when we had, if we net force was 0, then that meant that the initial and final momentums were equal. Here, if the net torque is 0, then our angular momentum is conserved. So if net torque is 0, then we say that angular momentum is conserved. So again, if you have a particle and it has some mass and it has some v, so maybe it's better to bring this guy down here. So here's my object, my particle. It's got some mass and he's got some v, and he's moving around some location, some r from some central location, then it has some angular momentum, which is going to be the r cross product with the momentum. So r, the momentum is m times v, and so I can bring the m out because it's just a scalar, and I end up with m r cross v, where again r is the vector from the axis, right? So this would be my axis and to the particle's location. I think we're going to do an example of that. If you have a large object that's just spinning around something, so let's say I've got, I'm not going to do my circle for that. Say I've got some sphere and it's spinning around some axis here. So pretend this is like the Earth, I guess, or a ball or something. And it spins around some axis, where this is our North Pole and our South Pole. Then that object has some omega that they're spinning at, and they have some moment of inertia, which is, their moment of inertia, which you have to go figure out from the table. And then so they'll have an angular momentum that comes from that spin. So let's do this problem really quickly. So number 33 from chapter 11 says that time equals 0, a 3 kilogram particle with velocity, and it gives it to us in unit vector, and it tells us its position. It's pulled by a 7 Newton force in the negative x direction. About the origin, what are the particle's angular momentum, the torque acting on the particle, and the rate at which the angular momentum is changing? All right, so this is a fairly complex one. So first we know that the mass, switch over to this. So my mass is 3 kilograms. And then they tell me that the velocity, and I'll write it in unit vector notation, is this. And then I'm actually going to write an R2. So I'm going to write the position from the origin. So it's at 3 meters in the I direction and 8 meters in the J direction. So that's my R. And I know the mass. So I can do the first part right here. So the angular momentum should be the mass and the R cross the V, right? That's what I just had over here. So the angular momentum for a particle moving around some location, and they want to know the origin, is mass times the cross product of R cross V. And just to give you an idea of what we're doing here, so if I have, this is my XY plane, we're at, say, 3, the particles up here, where this is 3 and 8, and then it has a velocity which is 5 meters per second in the x direction, so it has a Vx like this, and then a Vy which is -6. So its velocity is like that, its total velocity. And the R vector here is this, right? It's from the origin to our particle. The V vector is this. So those are the two vectors that we're doing the cross product of. But we can just use our rules for cross products. So we'll leave the mass. So the rules for cross products, if you only have I and J, right, we're supposed to do we want to go all the way back? Let's pause for just a second. All right, so this is all the way back to chapter 3. So here's A cross B. And all we have are all the z components are 0 here, right? We don't have a v0, vz is 0, and rz is 0. And all the parts, the part that would have the I hat have z components, bz and az. The j part has az and bz. And so it's really only this term that still exists. ax times by minus bx times ay, and all of that's going to be in the k or z direction. So I can write this out and I can say, well, this is vx and vy and rx and ry, and r is our a. So I should do rx times vy, and then I should subtract vx and ry, and that will be in the k direction, right? Ax is rx, by is vy, bx is vx, and ay is ry. So going and plugging in these numbers, I have 3 kilograms times Rx, which is 3 meters, times Vy, which is a negative 6 meters per second. So those are all multiplied together there. And then I'm going to subtract Vx, which is 5 meters per second, times Ry, which is 8 meters. It should probably be like that. So let's not do our ask yet. So here I have 3 times negative 6, so I have negative 18 meters squared per second. And then I'm subtracting 5 times 8, which is 40 meters squared per second. And so I end up with negative 58 times 3. Negative 58 times 3 is negative 174. And the units are kilogram meter squared per second, which is actually true. That's are the units for angular momentum. Maybe we should have written that down over here. So the units have to come out from the R, you get a meters. From the momentum, you get a kilogram meter per second. And so the units for angular momentum, and again, there's no shortcut symbol for this or unit. It's just kilogram meter squared per second. It's one of the ugliest units we have. So I have a negative angular momentum. In other words, a negative angular momentum means that this would be clockwise motion. And that is what it is, right? If this particle is moving as we're showing in this velocity, that is clockwise motion, or in the clockwise direction. So I agree with the negative. It is that. And again, this would be technically with the K. I'll drop to my K somewhere there. And the negative K, that basically means clockwise motion. It's a weird way to talk about motion because you've got that K hat there, but that's what it means. Negative around the Z axis, which is sticking straight up out of the board, out of the paper here. So that's my angular momentum. The torque acting. So the torque acting, torque is R cross F. So again, my F, now it tells me that the F here, so let's erase this first. So my F, it says, is 7 newtons in the negative x direction. So writing that in unit vector notation, that's negative 7 newtons I. So again, I can sit there and I can just do, if I do R cross F, I've got my 3I plus 8J, and I'm crossing that with negative 7 newtons, or 7I, 7 newtons I. Here we can just distribute this. If I do 3 crossed with this I, that's actually going to end up being 0. So if I have I cross I, that's 0. So all that really matters is the 8 meters in the J direction. So I have 8 meters times negative 7 newtons. All of that is J cross I. Now numerically that ends up being a negative 56 Newton meters. And the direction, if I do J cross I, my hand actually ends up going, I end up with a negative K again. So J cross I is negative K. And we could go back and find that here as well. The right-hand rule, I cross J is positive K. J cross I has to be the opposite, has to be negative K. And so this actually is a negative K. So this ends up being 56 Newton meters in the positive K direction. I could actually sort of see that. Let's see. So this is getting a little busy up here, but if I really had a force, so I have the velocity drawn, but the force is supposed to be, let me erase this so it looks a little less busy. The force is supposed to be 7 newtons in the negative x direction. So the force is like this, right? 7 newtons. So if I did the right-hand rule here, where my fingers go in the direction of R with my right hand, and then I curl my fingers in the direction of the force, my thumb is sticking out of the paper. And that is positive, that's the positive Z direction. And so I do have a force in the positive, or a torque in the positive Z direction. So the force is trying to make this thing move counterclockwise, right? The velocity is currently got it moving clockwise, and so we have a negative angular momentum. But this applied force that we're putting on it is trying to make the object move counterclockwise, and so it's going to be a positive torque. All right, the last part, part C, and I'm going to have to add another page here. So part C, before we go to it, is the rate at which angular momentum is changing. So part C, rate of angular momentum change. Well, that's dl dt, right? That's the rate at which the angular momentum is changing. Well, the rate at which angular momentum changing is the net torque. So this is just the same number. It's my 56 Newton meters, but when we write it in terms of angular momentum, we should probably write it as kilogram meter squared per second squared, because the angular momentum has units of kilogram meter squared per second, and then if we divide that by the unit of time, we end up with another second, and that's where the second squared come from. You don't have to, but I think that's more appropriate. So this is changing by 56 angular momentum units for every second. and it's actually, you know, increasing it. So if this force continues to work on this object, it's going to change it to having a positive angular momentum. It's trying to make that angular momentum more positive every single second. So after 1 second, this is going to be, you're going to add 56 to this, and after a certain amount of time, this is going to end up being a positive angular momentum. Okay, so that was number, yes, that was number 33. I'm going to do these next two, and that'll be the end of these videos in part 5.